Ooh, wow. Fridays are getting scarcer and scarcer around here. Well, I know there'd be more people here a week from today. Nothing like a test to guarantee attendance. I know Jenna's frolicking in Orlando right now. All right. Okay. So the test is a week from today. I put 16.2 to 16.6. The only reason I didn't put 16.1 is all that does is talk about what a vector function is. So that's so basic to it, I didn't even include that. And you've got the review problems there from the text, and this weekend I will be posting online the solutions to the review problems. I think, and then there's the take-home quiz that's due that day. I think between doing the take-home quiz problems and doing as many of the review problems as you can, I think that will be a good preparation for the test. All right, and then I wanted to make sure, Jerry, I wanted to make sure that they do understand that for not only for the test that's coming up, but also for the final exam, that they can have with them a front and back of an 8.5 by 11 piece of paper where they can put down formulas, whatever information in their own in their own handwriting. Okay, and what I'd also, Jerry, what I'd also like them to do, like you to do, is that when you collect the test, also collect that paper and just tuck them into each person's test set. Okay, great. And when the Eureka people get online, because they're not online yet, I'll also let them know that. Okay, great. The homework, now I deliberately put the homework off until Monday the 5th because that's just a lot of stuff. So if you need extra time for the homework, I mean, you can certainly turn it in on Friday, but otherwise you've got a couple extra days to do the homework because Monday the 5th is officially our last day of class. So you can have a couple extra days. All right. So what we're going to cover today, we're definitely going to get through this 16.5. And the 16.5 covers two topics, curl and divergence. And for the curl purpose, it ties in a vector field being conservative with the computation of the curl. So we'll get to that. So first of all, let's start with the curl and let's look at its definition. So we're talking about a force field or a vector field. Now here we are now for this section, we're talking about 3 dimensions here. Okay. So we've got a force field that's equal to some function p times I plus some function q times j plus some function r times k. So it's 3-dimensional. The curl is defined like this. The curl of f is equal to, and it's a big long formula, the partial derivative of r with respect to y minus the partial derivative of q with respect to z, close parentheses, and this is the I component. We get a vector. This is a vector that we get. And then we have the next component. This is the partial derivative of p with respect to z minus the partial of r with respect to x. And that's all multiplying the j vector. And then finally, the third one is the partial derivative of q with respect to x minus the partial of p with respect to y, and that's multiplying the k vector. All right. So thank goodness we don't have to memorize some formulas here. However, I'm going to show you a nice kind of memory aid for this that I do encourage you to utilize. So we're going to look at this memory aid. All right. Now, to introduce this memory aid, I have to introduce this one concept called the del, D-E-L operator. And it's represented, and it is another one of these upside-down triangles, all right? And it's equal to the following. The I vector times just this, delta, delta x. There's no function in there. Plus the j vector times delta, delta y, plus the k vector times delta, delta z. Now, obviously, in and of itself, this is meaningless because we don't have anything that we're applying the partial derivatives to. But we can apply this to a function. We can also apply this to a vector even. So apply this to a function. Let's call it a function little f, and we get this. We get upside down triangle f, and of course we've seen this before. This is the gradient, right? And let's see that we do indeed get the gradient. I'm taking this whole thing and I'm applying it to the function f. So what we get then is this. I, the vector I, times the partial derivative of f with respect to x. Now I'm applying this to my function, plus the vector j, partial derivative of f with respect to y, plus my vector k, partial derivative of f with respect to z. And this is, of course, exactly the same thing as the gradient. This is equal to, of course, a vector. The first component is fx. The second component is fy. The third component is fz. All right. So this is what's called an operator, which means we can apply it to a function. All right. Now, what I want you, now for this memory aid, I want you to think of this operator as a vector. Now think of this del operator as a vector, i.e., del is equal to, first component would just be delta, delta x, delta, delta y, delta, delta z. Okay. Again, in and of itself, this is meaningless. But for this memory aid that I'm going to show you, it does have meaning, okay, if in the memory aid. Okay. What we're going to do here is we're going to use this, and I'll put this in quotes, we're going to use this vector and do a cross product with our vector field. and do a cross product with our capital F, which remember, our capital F is the vector, first component is a function of P, second component is a function of Q, third component is a function of R. So let's see what we're talking about here, about this cross product. So we're talking about this operator del cross our vector field F, right? Now, this you have to remember from when we did cross product of three-dimensional vectors how we did this. Remember, we put our vectors, our unit vectors I, J, and K in the first row, and then we put the components of the first vector, and then we put the components of the second vector in the next two rows. Now, this first vector is just this delta, delta x, that first component, delta, delta y, delta, delta z. All right. Yeah. Yes, cross product. It's a cross product. Right, cross product. Okay. And then our last row is the second vector here, which is our functions P, Q, and R that compose our function, our vectors. Now, let's calculate this. Remember, we use a determinant with this. All right. So what I tell you to do is to go across the first row. So go across the first row. So our first element there is I, the vector I. And then we're going to multiply that. Remember what we multiply it by. We blank out or mentally remove that first row and that first column. And let's see what we have left here. Then we do the determinant of the 2 by 2 matrix that is left. Well, here's the 2 by 2 matrix. Delta, delta y, R, then Q, delta, delta z. So you think of it this way. Okay, we in a sense multiply these two together, but you're really not multiplying it. You're applying that derivative to the R right here. You're going down. So that's delta, delta y of the R function. And then, of course, with the determinant, then we subtract, and then we look at the up diagonal, which can be looked at as applying the delta, delta z to the Q function, minus delta, delta z times the Q function. And before we go further with this, let's just look at our original definition of the, oops, what's going on here? Okay, of the curl, and the first component that we've come up with here matches, of course, the first component that we have in our definition, all right? Everybody see that matches up. All right, so let's just complete this determinant. Now, this is something that I found on a couple of homework papers that I want to make sure is clarified, that when we're going across this on this second component, we have to introduce the second component with a minus sign. And then we put the J vector there. With determinants, you alternate plus, minus, and plus. So be sure we introduce a minus sign there for that second part. And then, of course, then we're blanking out that first row and now the second column, rather. And what we have left, then we do the determinant of what's left, and that's going to be delta, delta x applied to R minus delta, delta z applied to P. Okay? Go down diagonal minus the up diagonal. So let's mark this down. Delta, delta x applied to R minus delta, delta z applied to P. Oh, wait a minute. Hold it. I think I messed up something. Go down to C. Yeah. Oh, yeah, that's right. Okay, now let's compare this one to what we had in our original definition. Our original definition for the second component with the j vector is delta p with respect to z minus r with respect to x. Now notice here on the inside we have r with respect to x minus p with respect to z. They're reversed. However, we have a minus sign in front, so this component truly is delta r, I'm sorry, let's do the delta p, delta z, change the sign, minus delta r, delta x, applied to the j vector. Okay, we just make sure we change the sign, and we get the same thing. And then finally, we go to our last component in the first row. This time we do a plus sign, plus our k vector. And then we block out the first row and now the third column. And what we have left going down diagonal is delta q, delta x. And then subtract the up diagonal, that's delta p, delta y. Okay. So we're going to have delta x applied to q minus delta y applied to p. And then that is this, well, yeah. That is the very same thing that we have in our definition for the curl, all right? So I think this is, now of course, if you can certainly just, as you can write this on your paper, you can certainly just operate off of the definition that you've written down, okay? But this is a good memory thing in case you didn't have a paper to work off of, all right? Okay. So what we have here then, so we can say thus, we can say the curl of some vector f does equal to the del function cross product the vector. Okay. So this is perhaps something that you might, I would suggest you might want to note that the curl is equal to that. Okay. All right, so let's look at a specific example here so we can just work with something concrete. Let's say our capital F vector field is equal to x times z times the I vector plus x, y, z times the j vector. Oops, that should be a minus y squared times the k vector. All right, and we're told to find the curl. All right. Okay, so I'm just going to do it with the memory aid. So we're going to have our 3 by 3 here. I'm going to, at the top, I'm going to have I, j, and k. On the second one, I'm going to have my delta x, delta y, delta z. And then on the bottom row, I'm going to put my components x, z, x, y, z, and minus y squared. Okay. All right. Okay, we go across that first row. Okay, I start out with the I vector. And let's see what we get here then. All right. The first thing we're doing then is we're doing the derivative with respect to y of negative y squared. Going down the diagonal, well, that's equal to minus 2y. Okay. Then we have a minus sign because we're doing looking at it as a determinant. And then we subtract the derivative with respect to z of xy times z. So that's going to be, the z is going to go to a 1. That's going to be minus xy. Okay. So that's our first component. Then with the second component, we remember we have to put a minus sign in front of the j vector. And let's figure this out. Now we're blocking out the first row and the second column. So now going down the down diagonal, we have delta delta x of negative y squared. Well, y is a constant, so that's going to be a 0. And then we minus, and then we look at delta delta z of x times z. Well, z is going to go to 1, so that's going to be an x left over. Okay, so we have that. And then we go to our last component, the k vector. We block out the first row and the last column. And we have delta delta x of x, y, z. X will go to a 1, so we'll be left with y, z. And then we have a minus. And then on the up diagonal, we have delta delta y of x times z. Well, they're both constants, so that is a 0. Okay. So this is what we have, and now it's just a matter of cleaning this up a little bit. Our first, let me write it even with just this bracket notation. Our first component is going to be minus 2y minus xy, comma. Now be careful with the second component. We have this minus sign in front. We have to apply to it. So it's going to be a double minus x. So I'm going to have a plus x there, comma. And then our third component is going to be yz. So that would be the curl. Okay. Now, there's an interesting fact about the curl, and that's this. The book has a nice little proof on this, but we'll just, you can look at that if you like. If we're given a function of x, y, and z, then the curl applied to the gradient of, I should put an L there, the curl applied to the gradient of f, remember this is a vector, is equal to 0, but not the number 0. Remember, the curl is a vector. It's equal to the 0 vector. So 0 with that arrow on top of it. So you might want to note this little fact also. You never know, I might slip some few of those fun true-false questions down. Mary's going, oh no, not really. Okay. Now, so this kind of leads to the next thing. Okay, the curl of the gradient is equal to 0. But remember, if capital F is a conservative vector field, then that means capital F is equal to the gradient of some little f function, right? And therefore, if capital F is a conservative vector field, its curl will equal the 0 vector. So let's get this stuff down. If capital F is a conservative vector field, then that means that capital F is equal to the gradient of some small f function. So the curl of this conservative vector field, well, if capital F is equal to the gradient, so therefore the curl of capital F will equal the curl of the gradient of the small f. And from the fact we just talked about, the curl of a gradient is equal to the 0 function. Okay. And this is how, remember we had the test in 2 dimensions. We had that test for whether a vector field is conservative or not. For 2 dimensions, if our F was equal to P times the I vector plus Q times the J vector, then we found out that F is conservative. It was if and only if. What was that? It was if delta Q with respect to X is equal to delta P with respect to Y. Right? Okay. Well, that was our test for 2 dimensions. What we're going to use for 3 dimensions to show that a vector field is conservative is to use the curl. Okay. So a couple of facts here for starters. Fact. One thing we can say is this. If the curl of some vector field F doesn't equal 0, then we know that our vector field F is not conservative. All right, that would follow from what I had just put down. So let's just look at an example of this fact. Show that F equaling the following. Let's see. The first component is xz. In fact, this is the one, wait a minute, this is the one we just worked with. Yeah. xz, xyz, and minus y squared show that it's not conservative. Okay. Well, we just had gone through the example and found out that from the previous example, the curl of this vector field was, what was it? First component minus 2y minus xy. Second component was x. Third component was yz. Well, certainly this is not a 0 vector because x and y can be any value. So therefore, this does not equal the 0 vector, so it is not conservative. Okay. All right. So then let me put this next fact down, which is something I've already stated verbally, and that's this. So this is how to show a 3D vector field is conservative. Okay, we use this fact. And this fact kind of works in the other direction. If F is a vector field, defined over all of R3, so in other words, what that means is for every combination of x, y, and z, this vector field has a defined value. Then, and the curl of the vector field is identical equals the 0 vector, then we can conclude that F is a conservative vector field. And the thing is, we certainly like conservative vector fields because when we calculate their line integrals, all we have to look is the value of the little f function at the end of the line and minus the value at the beginning of the line. Okay. Okay. I'm going to put some stuff up here for the Eureka people that have joined us. Annalie I'm going to put some stuff up here that I had typed in at the beginning. Let me copy it here. Okay, let's see here. So that's reminding you to turn in the homework today. You should have available to you a take-home quiz and another homework set and a review set. The take-home quiz is due on this coming Friday, and that's when the test is going to be on 16.2 to 16.6. The homework, I'm delay making that due until Monday the 5th of May, which is our last day of class. And I'll be posting the solutions to the problem set, the review problem set, this weekend. Okay. Another thing I want to make sure that you pass along to your fellow classmates is this. For the upcoming test and for the final exam, you can use the front and back of an 8.5 by 11 blank piece of paper and use that, put any formulas or information you want on that and utilize that during the test and the final exam. So would you then also make sure that other students that may not be there right now receive that information? Okay. All right. Okay. All right. Thank you. Okay, before we take a break here, I want to do one example here with this fact about if the curl is 0, then we have a conservative vector field. So here's an example. It's got 3 parts to it, so there's 3 things we're going to ask. The first thing we're going to ask is this. A, show that capital F, which is equal to the following, y squared z to the third, comma, 2xy z to the third, comma, 3xy squared z squared, show that this is conservative. Okay, so we're going to calculate the curl of F. All right, so we start out with our I, J, and K, and then we're going to put our operators here, delta, delta X, delta, delta Y, delta, delta Z, and then our last row is going to be our components, y squared z to the third, 2xy z to the third, 3xy squared z squared. All right. Okay. So what we're aiming for is we're hoping that all 3 components are identical to 0. So let's start with going across the first row, start with the I, and then cover up that first row and first column. So what we have here then is we're doing, on the down diagonal, delta delta y of 3x y squared z squared. So y is our only variable there, so that's going to be, I'm going to take the derivative of y and leave the other ones alone. So that's going to give me 6xy z squared. All right. And then we have to go to our up diagonal and minus then. Up diagonal here is going to be the derivative with respect to z of 2xy times z to the third power. So z is our only variable, so I do the derivative of z, and I get 3 times 2 is 6xy z squared, close parentheses. Okay, so we see right off the bat these are both the same components, so I have 0 for my first value there. And then we do a minus j for my second one. And let us cancel out the first row and the second column. So we have delta x of 3xy squared z squared. X is our variable. It'll go to a 1. So we're going to end up with 3y squared z squared. And then we have a minus. And then we look at our up diagonal. Delta z of y squared z to the third. So z is my variable, so that's going to be 3y squared z squared. Close parentheses. And so again, we see we have the same terms subtracting, so we get another 0. So it's just left now to the third component, the k, and let's block out the first row, third column. So now we have delta x of 2xy z to the third. X is my variable, so that leaves me with 2y z to the third minus, and then we do the up diagonal, delta y of y squared z to the third. Y is my variable. I'm going to get 2y z to the third. Another 0. So therefore, my curl is exactly equal to the 0 vector, so therefore it's conservative. Okay. So that's the first part of this problem. Now the second part is this. Now that we know it's conservative, what that means is that there is a little f function such that capital F equals the gradient of the little f, all right? So for part B, and fully expect to have something like this a week from today, like this, find little f of x, y, and z such that our capital F is equal to the gradient of that little f function. All right. Okay, well, we know that this gradient is fx, fy, and fz, little f rather. So match up the components, equate the components. So for starters, I have little f of x, little fx is equal to my first component of the capital F, which is what? Y squared z to the third power. And let's match up the rest of them. My second component, fy, is got to be equal to my second component here, 2xy z to the third. And my third component, fz, has to equal the third component, which is 3xy squared z squared. All right. Okay. So what we have to do with each one of these three is do that partial integration. So for the first one, I do the derivative of fx with respect to x is going to be equal to, the antiderivative is going to be equal to the antiderivative of y squared z to the third with respect to x. All right. Now, the left-hand side from fundamental theorem of calculus, the derivative, the integral of a derivative is just going to be my function, little f. Now, on the right-hand side, I'm integrating with respect to x, so y and z are considered constants. And so we figure out what our antiderivative is. Well, it's just going to be y squared z to the third times x, right? We just tack on an x with this. So my little f is going to equal y squared z to the third x. Now, it's possible that what we could have in addition to this is a function just of y and z, which were considered as constants. So I'm going to say, okay, we could have a plus little g maybe of the functions, of the variables y and z. That is a possibility. Now we're going to do the similar kind of thing with the other two. So my fy, I'm going to do the antiderivative of fy, this time with respect to y, and I'm going to do the corresponding antiderivative of 2xy z to the third, also with respect to y. And then again, that left-hand side is just going to change into my little f function. On the right side, my integrate with respect to y, so x and z are constants. Okay, so the only thing there that's a variable is the y, and I do its antiderivative, which is y squared over 2, and we're going to have the 2's cancel out. So this is going to end up being x, y squared, z to the third power. And then again, it's possible we could have another function tacked onto it that consists strictly of our constants. I'll call that little h of x and z. Right. Now, hopefully you're alert enough to already see that we have a match here, right here. Okay, that first term, there, it's the same. All right. Okay, let's go and do the third one now. So we have, now this time we take the fz, do its antiderivative with respect to z, equals antiderivative of 3xy squared z squared with respect to z. Okay, so the left side again reverts to just little f, and on the right side, integrating with respect to z, so x and y are constants. And so z's are my only variable. Its antiderivative is going to be z to the third over 3, but now my 3's are going to cancel out. So I'm going to be left with xy squared z to the third. And then again, it's possible we could have some function, I'll call it I, of just x and y. Now, as it turns out, we really don't. Now what we do is, once we've done that, we compare all the little f's, all right? And we see that all of our little f's have that same component, xy squared z to the third, in all three of them, plus we have these possible other things. Well, in this case, those other things are just going to be a general constant, because we can always have a general constant as part of our antiderivative. So all of this tells me that my little f function is going to be x, y squared, z to the third, plus we could have some general constant, I'll call it capital K. All right. The book, if any of you actually look at the book on this, they do this a little bit different way. I think this way is a lot easier than how the book does it. Tom, have you looked at the book on this, on how they've done this?
What is?
Oh, gotcha.
Oh, it's coming the whole
Okay. All right. That's where we're finding that little f function.
Oh, okay.
And you have to do the antiderivative.
And you find like the d prime.
No, that's where the book. So I can tell you've read the book. This is a different way of doing it. It's easier. Right. Okay. All right. I have a third question with this, and then we'll take a break. So that was part 2. Part 3 then, letter C, is let's do this then. Evaluate the line integral on the curve C of f dot dr. And now what is our C curve here, where C is a line segment that, let's say, that begins at the coordinates 1, 2, 1, and ends at the coordinates 2, 3, 1. Okay. So of course that capital F, that's our this is our conservative vector field. So this is conservative. So the nice fact we know, and this is from that section 6.3 on the fundamental theorem of line integrals, is that if that's a conservative vector field, this goes for either 2 dimensions or 3 dimensions, that this value of this line integral is going to be, we take that little f function that we have now just found, and we plug in, first of all, the end value of the curve, the end coordinates of the curve, which is 2, 3, 1, and then we subtract, again, the little f function with the beginning coordinates 1, 2, 1. And that's all the calculation that we're going to have to do now to evaluate that integral. So we plug in this 2, 3, and 1 into our, let me write up here what our little f function was. It was x, y squared, z to the third, plus k. Now the thing is, for this purpose, let's just have k be 0, all right? Because it would cancel out anyway when we subtract. So just let it be 0. So we just plug in, okay, 2, 3, 1 into x, y squared, z cubed. So that's going to be, excuse me, 2 times 3 squared times 1 to the third power minus, and then at 1, 2, 1, 1, 2 squared, 1 to the third power. So I think we get 2 times 9, 18 minus 4. So our answer is 14. Okay. All right. Why don't we take a 5-minute break then? Yeah, just put it. Looks like a perfectly wonderful day outside. How was your test?
Alright. We didn't get to take home test, but it's not gonna be until Tuesday. Just make it do it on Monday. So I'll try up there a separate day starting there.
Oh, because you aren't normally there on Monday.
Right.
Right. But that's the official last day of class.
We don't have our final Thursday, it's like that will let me turn in Thursday.
Interesting. The thing is, if you turn it in on Monday, does that mean he's planning on having it graded when you go and take the final?
I didn't see why this one graded, that's graded on Monday.
Yeah. Well, everything that's going to be graded has to be graded by the 14th of May for the community colleges. I can tell you that. Because that's when grades have to be turned in.
I wonder what he's going to do with all this homework. Probably.
It could end up in recycling. You never know. Okay, one thing, and for those of you who are going to be taking physics or have taken more physics, the question is, well, gee, why do they have the name of this vector? Why is it called the curl? And the thing is, okay, so we have some vector field that's capital F, and we take its curl and we get a single vector. Okay, so say our vector field represents either airflow or fluid flow or something like that. So we've got a vector field that's kind of moving like this, for instance. Who knows, something. And basically, if the curl is then basically the vector that just out of that, these can be seen, this fluid, this is our F right here, our underlying vector field. If those are somehow rotating around in some fashion, such that if you could put a little tiny paddle wheel in there, and it would tend to float, say it tends to go in the counterclockwise direction, then the curl would be going up from that. The deal is this: the curl, we use what's called the right-hand rule. If our vector field is basically tending to flow like this, the thumb is sticking up like this. This direction of the thumb is the direction that the curl would be in. Now, say we have a vector field that's going the other way. Well, how about making it go the other way? That means it would be like this. So it's floating like, it's curving like this. So using the right-hand rule, then, our curl would be going down in the other direction. So the curl would be going downward like this, all right? So it has a relationship to the rotation of the flow of the underlying vector field, okay? So that's the reason it has this name curl. And for those of you taking any kind of physics, mechanical engineering, fluid dynamics, all that kind of stuff, I'm sure you're going to be seeing curl again, all right? next thing then in this section then, that's curl. The next thing is a concept called divergence. Okay. Now, curl gives us a vector. So I want you to understand that curl is a vector. This concept of divergence, this gives us a scalar or a number. All right. Okay. So how is divergence defined? Definition. So again, it's connected with a vector field. So we have capital F equaling some function P times I, some function Q times J, some function R times vector K. Then it's abbreviated div, div. The div of F, our vector field, is equal to the following. It's equal to the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y plus the partial derivative of the third component with respect to z. That's the definition of div. So these are all, this is a scale. Remember, this t is a scalar function. It's a scalar function. So this all, when you add this all together, this equals a scalar or number. All right. Okay. Now, basically, we can still use the del operator notation with this. Okay. So let's look at del. Remember, del is just this vector, supposedly a vector, delta, delta x, delta, delta y, delta, delta z. That's our del. If we look at the del dot product, our vector field F. Okay, what does this mean? Okay, the del is this delta, delta x, delta, delta y, delta, delta z. Dot, well, F is the function P, the function Q, comma, the function z. So remember, when we do a dot product, we multiply the first components together plus the second components plus the third components. Well, here in this case, we're not really multiplying it, but we're taking this first component, delta, delta x, and we're applying it to the first component here. So this is delta p, delta x. Then we go to our second component. We apply this to that second component, delta q, delta y. Then we go to the third component, delta z, that should be an R, not a Z, PQR, and that should be an R there, delta R, delta Z. Okay, so this is another way of representing the div, so we can have this fact, the asterisk, this one, the div of F is equal to the del dot the F vector field. Okay? So you might want to note that down on your paper for the exam. So let's look at an example of calculating this. This is pretty straightforward, I think. Let's have capital F of x, y, z equal x, z times the I plus x, y, z times the j minus y squared times the k. In fact, that's exactly the one that we used before, isn't it? Okay. And let's find the div of this f. All right. So the first function, xz, we do the delta xz with respect to x plus delta xyz with respect to y, and then plus, I'll do it this way, plus delta of negative y squared with respect to z. Okay, that's the definition of it, and let's see what we get here. Xz with respect to x, z is a constant, that'll just give us z. xyz with respect to y, well, x and z are constants, y is my variable, so that's going to be plus xz. Derivative of minus y squared with respect to z, well, that'll be 0. So this is our div right there. Okay. Let's see. Okay. Okay. So let's see here. So the curl of f, again, I'm writing this down again. The curl of f is a vector field because it gives us a vector. So since it's a vector field, we can apply the div to it. We can do the div of the curl of f. So we can compute the div of the curl of f. So what we do here, we calculate the curl of f first. We get that vector, and then we take the div of that, adding the various partial derivatives together. Well, this is the fact here. Fact, and you might want to also, there's all kinds of little facts here, so I'm glad you guys don't have to necessarily memorize all this stuff. So I'm putting an asterisk by this. The div of the curl of the vector field f is equal to 0. And this time the 0 here is a scalar, not a vector. Because remember, the div is a scalar. So there's another little fact right there. Then the last thing about the div here is, why is it called divergence? All right. Okay. Now, the div, or divergence, can be understood as a measure of how a vector field is spreading away from a single point, of how a vector field is quote-unquote spreading away from a point capital P. Okay. So how this can be measured is you can look at a point and pretend that you have a little sphere around the point and look at how much is flowing out of the sphere versus how much is flowing into the sphere. All right? So this, again, view it as either fluid or air, something that's flowing around. And if there's more flowing out of the sphere, view the sphere as like some kind of permeable membrane or something that things can flow through it, then the div will be positive. If there's more that seems to be flowing into the sphere, then it is, the div is negative. What is that word? There's a word called sink for if everything seems to be going in, and I'm blanking now on the word for when things are coming out. Sink, it's not sink and swim. It's, to look it up again. I didn't write it down. So actually, what I have here is some examples just to show you here. Because again, this is going to be for you future physicists, engineers, that type of thing. Let's look at three vector fields. And for right now, we're just going to look at, because it's easier to draw, let's just go to 2 dimensions here with this. And let's say the first vector field is just this, x, y. The second one is f is equal to y minus 2x for the first component and x minus 2y for the second component. And the third vector field is x is the first component, negative y is the second component. All right, let's calculate the div for each one of these. Now, remember, so for the first one, the div of f, that's the partial of the first one with respect to x, so that's dx, plus the partial of the second one with respect to y, well, that's dy. So this is 1 plus 1, so the div of that is 2. Let's look at the second one. Do the derivative, first of all, with respect to x, so the derivative of y minus 2x with respect to x, plus the derivative of the second thing, x minus 2y, with respect to y this time. And what do we get? For the first one, the derivative there is negative 2. And for the second one, it's also negative 2. So the div is negative 4. So for the first one, we have a positive div. The second one, we have a negative div. And then let's look at the third one here. The div is going to be, okay, delta x dx. And now we have plus delta of minus y dy. And that's going to be 1 minus 1, or 0. So it has a 0 div. So on Maple, I did a little vector field because it certainly can draw a heck of a lot better than I can. And here is the first one where the vector field is x, y. The div is 2. So what happens here is actually these vectors, as x and y get bigger, of course, the length of these vectors gets larger. But the div is a 2 all throughout the whole thing. It's a constant 2. So if we look at any point here, draw a some kind of circle around any point, what we would see here, and of course if we even had more arrows it would show it better, is that there's more coming out than there is coming in. Basically, we've got this whole area where it's coming out, and here where it's coming out, it has bigger x and y values, so it's going to be bigger values coming out. These are going to be smaller x and y values going in. So the net effect here is there's more coming out than there is coming in. So it's like I want to say source. It's sinking something else. Sink is when it's flowing in like to a black hole or something. But the other one is when it's coming out. So this is showing that we've got like this source of something coming out, and it's a positive div. Now the second one had a negative div connected with it, so that's this one right here. So we can see here if we basically, again, if we just draw a little circle here, what happens is that there's going to be more going in than there is coming out. We're going to have stuff coming in, less stuff coming out, and therefore it's a negative div. Okay. And finally, the third one where the div is 0, this is the vector field connected with it, and essentially essentially what goes in ends up coming out. So I guess there's a certain stagnancy about it then. What goes in is what goes out. Or it's just the same thing. There's neither a sink nor a source. It's just, I don't know. I'm not a physicist. But anyway, I wanted to point that out to you. I think that's kind of interesting. And that's the meaning of the divergence in physics. Okay, let's see. I think I will skip that. What I want to go to next here with this is the last part of this section. So we talked about the curl, we talked about the div. We talked that the curl means that it's a conservative, gives us that whether it's a conservative vector field or not. And it tells us something about the rotation of the vector field. The div tells us whether there's more of a going in rather than a going out. These concepts are also connected to Green's theorem. There is a connection. So, connection to Green's theorem. All right. Well, first of all, I think let's rewrite Green's theorem so that we remember what we're talking about here. Green's theorem is this. The line integral along a curve C, where we're dot producting a force times the unit tangent vector, ds. Well, this is the same thing as, there's a bunch of equivalencies here. This is the same as the line integral along the curve of from A to B. Now we can parameterize this from A to B of the force field applied to our parameterization dot the prime of the parameterization dt. Right, that's another way. This is where we parameterize and calculate it. Another notation then for this that I should have already written was the line integral along C of f dot dr. That's another notation for this Green's theorem. Anyway, what Green's theorem showed was that all of these things equal the double integral over the region D of dq dx minus dp dy. And now this is where the force field is represented as p times the vector I plus q times the vector j. All right. D here is the region surrounded by the curve C. And also I should have said here, C is a closed curve. All right. So we have C as a closed curve. It ends where it starts. This is our curve C. D is that region inside of that. So this line integral C of f dot dr is equal to a double integral along over that region of dq dx minus dp dy dA. All right. So that was Green's theorem. That's section 16.4. All right. Anyway, let's look at the connection with curl in this. Now, curl has to do with 3D. Curl is three-dimensional. But we can make this, and this up here, this was all two-dimensional. This is two-dimensional. If we look at our vector field like this, equal, okay, we have our first component is that t function, the second component was that q function, but let's somehow view it as a three-dimensional vector by putting the third component as just the number 0. So here, we're looking at F, our vector field, as a 3D vector, where the z component is just a 0. Now, doing that, since it's now a 3D vector, we can compute the curl of this new way of writing the f function. So we do it, we do the I, the j, and the k, and then we do our delta, delta x, delta, delta y, delta, delta z, and then our last row is the p function, the q function, and now that's just going to be the number 0. All right, and let's see what we get from doing this. First of all, we look at the I, and we blot out everything here. And now remember, p and q are functions of x and y. I need to put that in here. They don't have any z in them. We're strictly talking two-dimensional. So I have the I block out the first row and the first column. What I have, first of all, on the down diagonal is the partial derivative of 0 with respect to y. Well, that's going to be 0. And then on the up diagonal, we have the partial derivative of q with respect to z. Well, q doesn't have any z's, so that's also 0. So the component of I is going to be 0. And then we do minus j, and let's see what we get there. Let's blot out the first row and the middle column. On the down diagonal, we have, again, delta x of 0, well, that's 0. And on the up diagonal, we again have delta z of p, which only has x and y. So both of those are also 0. So the only thing we have left, then we have a plus, we have the k, so we blot out the first row, the third column, and we have this. On the down diagonal, we have delta q, delta x, minus, and on the up diagonal, we have delta p, delta y, minus delta p, delta y. So, of course, so we have here the curl of this f is equal to, let's just write it like this, delta q, delta x, minus delta p, delta y, and that's all multiplying the k vector. Okay. All right, so this ought to look familiar here from the Green's theorem, because Green's theorem involves the delta q, delta x, minus delta p, delta y. The only thing that's different here is that what we got here was this is a vector. That, of course, is not a vector. It's just a scalar function. So I can make that last thing a vector by doing a dot product with the vector k. So curl of f, if I dot product it with the vector k, well, what k is a unit vector, what is the vector k dot product with itself? What is that going to equal? Remember, this is 0, 0, 1, dot 0, 0, 1. What are we going to get? Going to get 1, right? Multiply the components together, we get 1. So if I take this curl, which has this k in it, dot product it with k, that's then just going to become delta Q, we're going to have a 1, delta Q, delta X minus delta P, delta Y. All right. So we can represent now Green's theorem involving this curl now, because we have part of the formula for Green's theorem, delta Q, delta X minus delta P, delta Y. So I can say this. So Green's theorem can be written as the line integral of C f dot dr is equal to, okay, the double integral over the domain. But now, instead of writing just delta Q delta X in that, I'm going to write this side of the equation, curl of F dot the K vector, and that's dA. Right. Okay. So this, now this is, I will tell you this is an FYI, all right? So just to let you know that we can look at this Green's theorem in terms of the curl. The reason I'm mentioning this, but one reason I'm mentioning this, is that there's something we're not going to get to, but I want to at least mention it today. It's called Stokes' theorem. Green's theorem involves two dimensions. Green's theorem is 2D, all right? Stokes' theorem is three-dimensional. So, Green's is 2D. Stokes, that I'm going to write down in just a second, is 3D. It's essentially a 3D version of Green's theorem. All right. So this is Stokes' theorem in very much a nutshell. Okay. On the left side, we have a line integral C along a curve C. Now, in this case now, this is a closed curve, just like with Green's theorem, but now it's a closed curve around a surface that's floating in three dimensions. So it's a closed curve around a surface, capital S, that I'll just say is floating in three dimensions, all right? That line integral along that closed curve of our force field F, now this is a three-dimensional force field, times this tangent vector and ds, so this looks just like this looks pretty much just like the other side of our Green's theorem, except now we're talking about a surface floating around. This is equal to a double integral over our surface. So that's our surface now floating in 3D. And what we're integrating is just like what we had written here. We're integrating the curl of our vector force dot. Now this time it's dotted with a normal vector ds. Right. This here is a vector that's perpendicular to the closed curve. Is it perpendicular? No. Hold on a second. Let me look at this. And this is, I just want to mention this because I wish we could be getting to it, but we don't have time. Right. Yeah. This is a vector that's perpendicular to the surface. The surface, capital S. Now, actually, there's a lot of, let's look at this for just a second. I don't want to, because I know I'm kind of rushing on this, obviously. This is actually very similar to what we have found here in 2 dimensions. Again, I have a double integral. Here I have a double integral over a domain. This is a flat surface, a flat region sitting on the xy plane. It's flat. It's 2-dimensional, but it's flat. In Stokes' theorem, we now have this surface, 2-dimensional surface, but it's floating around in 3 dimensions. It's no longer flat, all right? We have the curl of F in both of them. This in here, it's dot product with the K vector. Now, the K vector, if we look at the xy plane, which is where our domain is, D, that K vector is in the Z direction, right? That is a perpendicular vector out of that flat region. Well, in the general case, this N that we're dotting with is a perpendicular vector to our surface that's floating around. Okay. So, the Stokes theorem is a 3D version of Green's theorem, or another way of saying this is that Green's theorem is really just a special case of the more general Stokes theorem. Okay. All right. Let's see here. All right. Okay, that's it that I want to cover on that section then. You'll need to be responsible for what you need to be responsible for is calculating the curl and the div, and also being able to find out find that little f function by doing the partial integration. All right. Now, because this time I want to just do per usual and go to the last second. I know. Mary said, "Yes, I'm so glad." I can see it in your face. All right. I just want to get a start a little bit on the last section that we're going to cover here for the test. So we know how quick Mondays go by. 16.6. And we're talking about parameterizing, oh boy, boy, I'm botching that. Parameterizing surfaces. All right. So, we've seen how to parameterize the curve. In particular, a 3D space curve, we'll call it R of t. It can be parameterized as x of t times the I vector plus y of t times the j vector plus z of t times the k vector, where t goes from, say, A to B. So that's parameterizing a curve. T here is our parameter. Okay. We can do a similar thing to a surface. Now remember, a curve is one-dimensional. Even though it may be floating around in 3 dimensions, it's really only one-dimensional. A surface, even though it may be floating around in 3 dimensions, is 2-dimensional. Okay, so we can describe a surface in 3 dimensions by the following. Now this time we need 2 parameters because it's a 2-dimensional thing. So it would be R of U comma V, 2 parameters. And it's going to have an X, Y, and Z components. X component is some function X of U and V, that's times the I vector, plus a Y component, another function of U and V, times the J vector, plus a Z component, another function of U and V, times the K vector, okay? So what we have here is we have, now this time U and V are taking on all the values of a certain domain. U and V take on all the values of a certain domain. So here we have in 2 dimensions, we have U and V. We have some region here that we'll call D. And U and V will go through, take on all the combination of values here. So here we have a single point, U, V, and it'll be all these different values. Then this R function then, this vector, makes this into a 3-dimension, well, it's a surface in 3 dimensions, so we have X, Y, and Z. So it's some kind of surface that's floating around here in 3 dimensions. Every single point here, by use of this vector function, gets mapped into a point on our surface. So this point here would be our function, vector function R, applied to U and V. The components, though, of our surface are going to have 3 components. X, Y, and Z, because it's located in 3 dimensions. Now, these equations here, X, U, and V, Y, U, and V, and Z, U, and V, can be looked at as parametric equations. So first thing I want to say, S is called, let's call this the floating surface, let's call that capital S. S is called a parametric surface. And the 3 equations, X equal X of U and V, some function of U and V, Y equals some function Y of U and V, Z equaling some function Z of U and V, those are the parametric equations for S. Okay. So we have 3 sets of parametric equations. I'll do one example and then I'll shut up. Then we'll continue on Monday with this. Let's look at a sphere, just the outside of the sphere. So we're asked to find a parametric representation of the sphere x squared plus y squared plus z squared equals a squared. Okay. So we know that the radius is equal to the number a. Okay. Now, since we're talking about a sphere, the natural thing I'm hoping you would think of is that we would think of spherical coordinates to help provide our parameterization. Use spherical coordinates to provide the parameterization. Okay, for starters, for a sphere like this, we're not talking about the inside of the sphere, we're just talking about the boundary of it. There is a very simple short equation in spherical coordinates that represents the sphere. Does anybody remember what that is? Remember, in spherical coordinates, we have theta, phi, and rho. Yeah.
Rho equals the radius.
Right. Rho, that's the distance from zero, right? Or distance from the origin. So rho, in this case, rho equal to A, that represents our sphere actually. But that's not the parameterization we're talking about. We need X, Y, and Z. So this is something to recall from spherical coordinates, that the rectangular coordinate X, what does that equal? That's rho sine of phi times cosine of theta. Y is rho sine phi sine theta. And Z was equal to rho cosine of phi. So that's stuff that you had memorized for the last test. Of course, you could put that on your sheet if you like for, yes?
How do you use rho equals A if rho is, if the section of the sphere is zero?
I don't know, I'll defer that. Okay. So basically then, now all I'm going to do, since rho is equal to the number A, my parameterization will be this. X will equal the number A, which is our radius, sine of phi, cosine of theta. Y, my parameterization for Y will be A times sine of phi, sine of theta. My parameterization for Z, instead of rho, I'll put A times the cosine of phi. Notice here that we have two sets of variables. We have phi and theta. Those are our two variables those are the correspond to the U and V that I was talking about earlier. U and V, all right? So essentially, what we're doing here is we're mapping, let's see, let's put phi here and theta up there. We're mapping them to our sphere. Let's see, for this sphere, first of all, what would theta range between? What two values would theta range between? Yeah, it goes around, so 0 to 2 pi, that would be our theta. And what about that phi?
0 to pi.
Yeah, just 0 to pi. Remember, that's that angle from the positive z-axis. So that goes between 0 and pi. So we can have this. We have this rectangle here in that plane. Here is pi. Here is 2 pi for theta, and that every single point there with our parameterization maps into our sphere. Okay. So that's just one representation of how we can parameterize the surface. We'll start up from there on Monday then. Charles, I'll have to think about your question.
Right. So it feels like, for example, it feels like you're in x y equal to, it would be x squared plus y squared plus z squared, so you just do x minus whatever.
Right. Because you translate the x, y, and z, like x minus 2 plus squared plus, yeah, and so.
So how would you represent your root that isn't the origin of your sphere?
Yeah, yeah. Okay, and I think that's a good thing to look at. It's certainly entirely doable,